Welcome back. We're going to do chapter 10.7, Solving Inequalities. The first thing we're going to go over real quick is the strict inequalities and the or equal to inequalities. The strict inequalities we can see as less than, or we can see the flipped version of it is greater than. And we always remember treating them kind of like the alligator. It always faces towards the bigger thing because it's very hungry, right? And we could draw our little alligator. The or equal to inequalities have is less than or equal to, so it's got a line underneath it. And then you have the greater than or equal to. Now, when we go to kind of describe inequalities a little bit different, we're going to try to graph them. And when we graph, we're going to graph all possible solutions. And it's a little bit funky, so we'll start off with a nice guy. Let's say x is strictly greater than 1. So when we graph this, we're going to graph it on a number line. So here's our number line. Now, the purpose of this problem is comparing x to 1. X is everything bigger than 1, right? So looking at 1 somewhere on the number line, x could be, let's pick a value, maybe let's say 3. And we ask ourselves, is 3 greater than 1? And we say, yeah. So that's a possible solution. We could even be crazier, maybe further down the line we went to 1,000. Is 1,000 greater than 1? Sure. How about, let's say, 0? Is 0 greater than 1? No, that's not true. So we're not going to include them in our possible values. We could even go further down and try negative 10. And negative 10 is not greater than 1, so we don't include it. But now let's look at 1. Let's see, is 1 greater than 1? You'd say no. But how about 1.1? Is that greater than 1? Yes. So anything just past this 1 is bigger. So I want to exaggerate it, so I'm going to use an open circle saying I'm not including 1, because we just said 1's not greater than 1. But anything just beyond it and onwards, anything greater than it, is included. So there's the solution. Those are all possible solutions. We could pick any value in between here. There's 2 works. We could pick, 100, that works. Values that are shaded in on this blue line. Let's go ahead and try another one. Let's say the question asked us to graph x is less than 1. So once more, we'll draw our number line. 1 is the center of our focus. What I usually like to do is start off with, well, can x equal 1? Let's see, is 1 less than 1? No. So we're going to use an open circle. So we kind of devised something here. Strict inequalities have this open circle when we graph them. And soon we'll figure out what the or equal to inequalities have. So 1's not included. Now x is everything less than. Everything smaller than 1. So when we go smaller, we go to the left on the number line. If we want to go bigger, just like our previous example, we go to the right, in which we get larger. So let's try another one with this newfound knowledge. Let's say x is greater than or equal to negative 1. So we'll draw our number line. Negative 1 is the center of our focus. X is everything bigger than or equal to negative 1. So if I was to ask, is negative 1 greater than or equal to negative 1? You'd say yes. Negative 1 equals negative 1, so it works. Negative 1's not greater than negative 1, but it's an or statement, so one or the other has to work. So since it does work, I want to shade in that possible solution. So I'm going to fill it in with a closed circle. And now x is everything bigger, so when we go bigger, we go to the right. And there's our graph. And we could try the same deal for the reversed version. X is less than or equal to negative 1. We draw our number line. Negative 1 is the center of our focus. And sure enough, -1 does work, so we'll shade it in. It's included in our possible solutions, and it's everything smaller. So we go to the left. So, to fill in our chart here, we have an open circle for the strict inequalities, and for the or equal to inequalities, we have a closed circle that's shaded in. The first one is not including, because it's not part of the solutions. And the second one is including. It is part of our solutions. We shade in our solutions. Alrighty, so now that we know how to graph them, what we're going to do is learn how to state these a little bit better. And that's through set builder notation. We're going to start solving inequalities. And when we write a solution, we need a set of solutions. So this fancy notation we have going on here, we use curly brackets. The curly brackets describe to us the set of. The next thing you're going to see is some sort of variable. And whatever that variable may be, it's so that the set of all variables, whatever it may be, an x, y, there could be multiple in there. We're usually going to see one of them. And then there's this straight line bar. That means such that. So it's a condition. We're saying these variables work only if we have this last statement here is true. And whatever that statement may be, it has to be true. So let's go a little bit more in depth with that. If we, by some chance, have the set x such that x is greater than or equal to -1. The reason why we're writing this in this very particular manner is because there's many solutions that work. If you remember in 10.1 to 10.3, there was one solution, there was many solutions with all reals, and then there was no solution. This type of solution has many possible cases. So if I wanted to make a list of solutions, I'm going to have values for x. That's what this first part's telling me. X equals. But I have to be very careful. X can't equal anything I want it to be. It has to be very specific. Like 2 works. Because if I put 2 into this condition, 2 is greater than or equal to -1, checks out, so that is a possible solution. I could even try x equals, let's see, -1. -1 is greater than or equal to -1, so that's true, that's a solution. But I also know what are not solutions. And I should say this is only a list of some solutions. I'm sorry about that, because I only listed off 2. There's many more. So something that's not a solution, maybe x equals -100. If I have -100, is that greater than -1? No, -1's bigger. So this is not a solution, so x can't equal that. So that's why we have this special notation, because if we were to eventually try to graph this, and I'm going to squeeze this in up here, -1 would be at our center of focus. X is everything greater than or equal to, so all values to the right of -1 work for us, and anything to the left doesn't work. So it's not everything works, so it's not all reals, but it's not just one solution. We have multiple solutions here. So that's why we have this special notation for it. So let's go ahead, get some experience. Let's solve using the addition principle. Now before we tackle the addition principle, I want to take a really general example. Let's start with a true statement. Like, I don't know, 5 is less than 10. We can all agree about that. So if I manipulate this using the addition principle we remember from 10.1, we would say if I subtract 1 from one side, I better subtract 1 from the other side. And I'm treating my inequality as the two sides of an quote-quote equation, right? It's really an inequality, so it is still an equation of some sorts. What is 5 minus 1? 4. Is that still less than 10 minus 1, which is 9? Yeah, that's still true. Okay, let's see. Let's try something else. Maybe if I add things, if it messes with it. Maybe I add 1. And what I do to one side, I do to the other. So now I have 6 is less than 11. Well, that's still true. So if I subtract or add things, I don't change anything. That's the beauty of addition principle. It follows the same suit. Pretty much what we do to one side, we have to do to the other. Now, let's talk about multiplication principle real quick. Multiplication principle is not as nice. I mean, it's almost as nice. Let's start with that true statement. 5 is less than 10, which we can all agree on. And let's say I multiply both sides by 1. So I have 5 times 1 is 5. 10 times 1 is 10. Is 5 less than 10? Yeah, that's boring. I said the same thing. Okay, so I didn't change anything. Let's get a little bit dangerous. Let's say I have 5 is less than 10. And let's multiply both sides by negative 1. What I do to one side, I do to the other. 5 times negative 1 is negative 5. And 10 times negative 1 is negative 10. Is negative 5 less than negative 10? No, that's not true. That's wrong. Negative 5 is greater than negative 10. So there's something that must be said whenever we multiply or divide by a negative number. We have to flip the inequality. So let's put that into writing. And I'm going to try typing that. If you multiply or divide by a negative, and now you can see how I cannot spell, then you must, and we're going to use this in quotations, flip the inequality. Okay, so let's go ahead and see some examples of this. We'll start off with a nice one. Here's our first one. We have 8x is greater than 32. Well, there's no negatives in sight, so if we wanted to solve this, we'd have 8 times x. In order to undo it, we divide both sides by 8. So we have x is still greater than 4. And we'd write this in set builder notation. We have the set of all x such that this statement is true. Alright, that one was nice. That was very nice. So let's try another one. Let's get a little bit crazy. Let's say negative 8x is greater than 32. So we have negative 8 times x. In order to undo it, we divide both sides by a negative. And here's where that rule comes into play. If you divide by a negative or multiply, you must then flip the inequality. So we have x is now less than negative 4. And we'd write our solution as the set of all x such that x is less than negative 4. Alright, let's see one more. And this one's going to be tricky, so if you want to pause it after I write it, try it on your own. We have 8x is greater than negative 32. So go ahead and pause, give it a shot. Alright, so we have 8 times x. So in order to undo it, we divide by 8. And what we do to one side, we have to do to the other. Now, did I divide or multiply by negative? No. So I don't have to mess with it. Don't flip the inequality. Sure, there's a negative involved, but it's only if you divide by a negative or multiply by a negative. I did neither, so I leave it alone, and there's my solution. Alrighty, so that's nice. Let's go ahead and give a shot solving equations using both principles. So our first one we're going to tackle, we'll have a bit of a mess here, and we'll clean it up soon. Alright, we're going to follow the same steps we always do whenever we solve equations. We'll identify our equation, so to speak, our equal sign or our inequality. And we first simplify both sides as much as possible. So if there's like terms to combine, combine them. And sure enough, we have 8x minus 6x, which gets us 2x. And still plus 8, still greater than 12. After we simplify, our next step is to use the addition principle. And the beauty about the addition principle is we don't have to worry about flipping anything. It's all nice. We have a plus 8. If we subtract 8 from both sides, it doesn't change anything. So we have 2x is greater than 4. And then we have the multiplication principle. And the only time we have to worry about it is if we multiply or divide by a negative. Otherwise, life is still the same. If we divide by 2, we're dividing by a positive, so no worries. And we have x is greater than 2. So our answer is the set of all x such that x is greater than 2. Let's go ahead and do another one. Make sure we do absolutely feel comfortable with these. And this will be the last one we'll tackle. We have 13 minus 8y is less than or equal to y plus 40. So our first step is to simplify. We have two sides of the equation. We can't combine 13 and negative 8y because they're not like terms. Same deal for the right-hand side. We have y plus 40, not like terms, so can't combine them. We also have the dilemma where y is on two different sides. So we move usually the smaller one to the bigger one. Makes life more positive. So I have a negative 8y and a positive 1. This guy's definitely smaller, so I'll move him to the other side. And we have 13 still there. Didn't mess with anything, didn't multiply or divide, so we're in the clear. 1y plus 8y is 9y. After we've simplified and we got one variable on one side of the equation, we're going to do addition principle. Subtract 40 from both sides. 13 minus 40 is negative 27, is less than or equal to 9y. Now be careful. We have 9 times y, so we're dividing by 9. Are we dividing by a negative? No, so don't mess with the inequality, leave it alone. A negative divided by a positive is a negative, and we have 3 is less than or equal to y. Now, the only thing here is when we write this in set builder notation, we're going to say the set of all y, since that's the variable we're talking about, such that usually we like to see the y first, and the alligator's facing towards y, so alligator faces towards y. Y is greater than or equal to negative 3. I did not flip the inequality. I just rewrote it in a different manner. If you recall, we could write A is less than B is the same thing as B is greater than A. Keep that in the back of your mind. That's all I've done is rewrite the same statement. And that's it. That is your solution. So until next time,